Okay, so we've been talking about managing memory uh, on the heap for classes, and we talked about the rule of three: copy constructor, copy assignment, and finally the destructor. And that involves copying values from one region of memory to another region, and the destructor helps us eliminate or clear memory that we've created when our class goes out of scope. And that helps us, those three in conjunction will help us eliminate any memory leaks we can have. And today we'll continue talking about heap memory, and we'll talk about the move constructor and the move assignment. And those complete the rule of five, which is applies to the modern C++. That's 2011 and beyond. So let's get started with that. Let me see here. Okay, so I found it. So we're talking about a class override with no move constructor. So we know that we will encounter an issue, and we'll talk about how to get around that issue. Let me. Okay, so we're going to talk about overriding an existing class, and then we don't have that move constructor, and we're going to see what happens in memory, and then we have to fix that issue. Okay, so we have this piece of code here where we have our vector, and that's the vector we've been developing, and then we create another vector, but notice instead of copying we're using the move function, and that's from the standard library. Behind the scenes, the move will copy, not copy, switch pointers. Okay, but we want to see what happens here. So let's go to main. Let me see, main.
Professor, before you get too far, did you start the recording?
Yeah.
Okay.
Yep. Yeah, this time that's the first thing I did. Okay, so yeah, 3 minutes, right? 3 minutes and counting. So okay, so we have this code, and we'll run it, and we'll look at the output messages for our vector class. Remember, I've been adding output statements so that we can see what is executing, and then we can make sure we are diagramming correctly. So let me, why did I close that? CMake, source, examples, run. And again, why are we doing this? Well, I mean, these are rules that we have to implement anytime we are working with a dynamic memory in classes. Okay, so notice we have here constructor create memory. Okay, so let's look at main. Constructor create memory. Okay, execute copy constructor, this one, and then what happened here? Right, so we don't have access to the move function, so we can't go in there and create output statements, but we can diagram to see what's happening. Okay, so let's diagram, draw. Okay, so three elements. We can use some real numbers, right? 5b0, so we'll say 15b0. That would be on the heap, the 5b0. 1, 2, 3. Okay. And then we have 15c8. 15c8. Okay, and we'll also get 3 elements, so then you can go here, 3 elements, and what is it, 15c8, 15c8. Okay, one thing I wanted to do, let me see in the output. Okay, 15c8, 15b0. Okay, so that was good. But what we are after, without like taking the code into consideration, we're saying that we want to move v into v1, or we want v1 to take ownership of v. But what we are doing here, this is v's memory right here, so it's in existence, and then right here this is v1's memory. But if we think about it, like, there's really no reason to create this memory, because I mean, if we just want v1 to take ownership of v, then maybe v1 should point to that existing memory, and that'll save us memory creation and copies. Now, this is only 3 elements, so maybe some of you all are thinking, well, what's the big deal? It's only 3 elements. But we know with vectors, we can have like a very large list. So if we have a large list, even this should seem logical to us. It's kind of like, well, yeah, I mean, the memory's already there, so why shouldn't we just take ownership of it? Anyways, we're gonna invalidate this guy. Move, that's what I'll do. Move will invalidate this guy. This won't be pointing to anything, because we are saying let v1 take ownership of your memory. So we need to write some code that eliminates the memory creation and the copies of the elements. And then we are saving those memory creations and copies. And if we had a very large list, then obviously we wouldn't want to copy, say, like 10,000 elements, because I mean, they're already in memory. So why don't we just have the class that we want to move into point to that memory, right? So that's what we're doing here. So let's go and write the code. Okay, let me see here. So that is the move constructor, and the code is actually very simple. You go to the header. Let me write the code, and then I'll explain that symbol. Move constructor rule for a 5 modern C++, right? So this is rule for a 5 for the rule of 5. The rule of 5, and that applies to modern C++. Okay, but this we've not seen. We've not seen this, right? Double ampersand. We've not seen that. So let me briefly explain that. So if we have L value and R value, right? That's what I have to talk about here, our value. And I'll make it short. I just want to make sure that students understand. So we have stack. And then we have some other memory that I don't really focus on, but for this example, or for this concept, it's important that we understand that there's always other memory. So we say num equals 5. By now we know that this goes here. But where did 5 come from? So we know these ones are called literals. So C++ has special memory for literals, so it's here. And when our program runs, that's where the 5 comes from, right? But before today, it really didn't matter where it came from, right? So if we say, where's the ampersand? I'm not gonna try to draw it because I always mess it up. So if we say ampersand num, like cout ampersand num, then our program will compile. Let me make this larger. Our program will compile and it'll print the address of num. However, we cannot say ampersand 5. This will produce an error. Our program will not run, so that's an error. This is an L value. Why? Because we can reference its address. This is an R value. Why? Because we cannot reference its address, although we know it has an address because it's in memory, but we don't have access to that, okay? So that's an R value. And let's come back over here to the example. So if we're saying move V into V1, then V will become an R value. Like it's gonna go out of scope, but for those milliseconds that it's in memory, this double ampersand that we use here is asking C++, I know that I don't really have access to this, but temporarily while this constructor runs, let me have access to that object so that I can do something to it. And what we are going to do is we're going to steal its pointer to the memory. We're going to like take over, hijack the memory since it's already there, okay? So that's what the move constructor does. So we have, okay, let me copy this. And the code for the move constructor is actually very simple. We're just switching pointers. So let me come here and constructor, make it part of our class. Let's write the steps that we need to take to make this happen. And I have them here because I don't have them memorized. Okay, my notes here. Okay, so where are you? Here. So step 1, we need to, oops, not that note, this one. Get v dot elements memory. Step 2, get size from v. And finally step 3, point v dot elements to nothing, or the null pointer. In C++, if you assign a pointer the null pointer, then behind the scenes C++ is assigning it to 0, and that is telling C++ this pointer points to nothing. That way, if in the future someone tries to use it, then it's pointing to nothing, so nothing happens, okay? So that's what we need to do here. So let's see, get v dot elements memory. So we simply say, well, let's say first move constructor, and then we want to display the memory address. We need an initializer list, so we say, okay, I know step one is get v memory, right? But we've been using size, doing size first, so I mean putting it in the initializer list first, so that's what we'll do here, size v dot size. Okay, so we get the size from v, and then we get the elements from v dot elements. Okay, so that's steps 1 and 2, and then we're saying point v elements to nothing. Okay, v dot elements equals, we can say 0, but for modern C++, it's common to use null pointer. And if we set that to null pointer, then we better set size to 0. Okay, so maybe here v size to 0. Okay, so now that we've done this, then we are eliminating this memory creation, and now this pointer should point to over here. So if we come back and run this program, this is what we saw first: constructor, create memory, execute copy constructor. What we should see next is execute move constructor, and then we'll see what the memory states. Okay, so let's go ahead and run that. Okay, so constructor create memory 15b0. Okay, well, thankfully it gave us the same memory, right? 15b0, 3 elements right here. That's this statement right here. Okay, so move constructor. Oh, notice same memory. Let's move up a little bit. Before the copy constructor executed, and the copy constructor it didn't do anything wrong. C++ was just trying to work with what we had, and what we had was creating duplications, right? So now that we have the move constructor, then this is eliminated and this is eliminated, and now we have this pointing over here, right? So if I copy this, Control C, and then we can write the diagram, and we can see that now we've eliminated the unnecessary memory creation. So we have 1, 2, okay, so that's what we have when that executes, and then when this one executes, then we are saying get the size 3, and then we're also saying get the memory 15b0. So initially we know that this was pointing there, but we set the pointer to null, so now that one's not pointing to that memory. But before we had done that, we're pointing there, so we won't lose the memory reference, right? That way we can clear that memory later. And then we're saying set this to null pointer or 0, and then set this one to 0. And now we have eliminated the unnecessary memory creation and move, and that's what the move constructor does for us. Okay. Let me see here. Okay, no questions. Okay, so that was the move constructor. So now let's move on to class copy with no move assignment. And for this one, we are after, let me see my main here. Okay. I have to write some free functions. So we're going to create a new function that returns our vector. So we simply name it getVector. Go to the CPP. This is a free function, okay? It's not part of our class. Vector v return v. In main, let me see. Maybe we name this one v1. v1. Okay. Or what should I name it? We have v. This is v1. I just want to keep the name separate. Well, it doesn't matter. We can name it v. Okay. And instead of move, then we say getVector. Okay. And let's diagram this piece. Okay, so we have that code. We have our stack. I have heap. Okay, so we have this one, size, 3 elements. I'll wait for the memory, right? We'll get a memory number from the computer, but we'll still use this one here. And then we have vector v1 equals get vector. Okay, so what happens in get vector? We create another vector. Okay, so let's diagram this one. So it's of 3, and we know that it also has elements. And then what happens here when we say equals v1? Okay, so this one, assume as it was here, and then let me draw more lines here. And then assuming this one, so equals temporarily create some more memory. So that will be 3, and I'll validate this by running the program. Okay, so let me see. If I remember correctly, that is what happens, but we can always run the program, and we have output statements, so then we'll track the statements. Okay, so let's run it. Okay, so let's inspect this. Okay, create memory. Okay, so get vector. Is that the right piece? Yep. So I created one unnecessarily. Let me see here. 0, 0. Let me double check that. Oops. v3. Okay, I'll get vector 3 elements, v1 equals get vector, so constructor, and I was pretty sure the copy assignment should have executed there. Let me see. This one. What did I miss? Oh, I know what I missed. I don't create a new vector. I say v equals get vector. Yep. So now I run in terminal, and now we should see a different output there. I knew that didn't look familiar. Okay, so let's inspect again. Okay, so now we have create memory 15BO. Okay, so let's update this. 15BO, and then we come back and then create memory again, and that's what's executing inside the vector. Okay, so that's this code right here, get vector. This one, get vector. Okay, so that one gets memory address 15C8. Okay, so 15C8. And then we go back and look at the output, and we see 15EO, copy assignment operator. Okay, 15EO. But as you can see, this guy, so let's diagram it properly. Okay, 15EO. 15BO, 15C8, and then let's investigate this to see what's happening in our move assignment. Okay, so copy assignment. Copy assignment. We create new memory. That's the green section. We copy the values from v.elements into temp, and then delete elements. Elements equals temp, size equals v.size. Okay, so let me update this code too, right? Because this one is to say this, like that. Okay, and then we trace the equal. Oops, Control Z. I wanted to use green. We trace the equal sign like that. Okay. So copy elements from this block to this block, and then it's saying to, oops, this one's wrong. This one has to be right there. Okay. Copy from 15BO to 15EO. We do that. And then it's saying to invalidate memory for V, which is this one. So then we're like, okay, I can do that. So this one is 0, this one is 0. I'm not pointing to that memory anymore. Instead, I am pointing to that memory, right? And this one is actually 3, and this one is 15EO. And let me again double check that. Copy elements, delete elements, elements equals new memory, size equals return this. Okay, yeah, we did that. And let me validate that diagram. Just did it yesterday. Let's see here. I just need to look at my notes, okay? Because this one, I'm not 100% sure of it, but I can double check right now. Okay, let me verify. Okay, so vector, get vector, yeah, okay, yeah, that diagram's correct. So, but again, we run into the same issue where it's kind of like, wait a minute, like this memory already exists. So why don't we take care of the issue, right? Where, I mean, we just hijack the memory instead of creating memories and copying values from old memory to new memory. We're creating unnecessary overhead for our program, right? So let's go ahead and fix that. And we fix that by creating the move assignment. Okay, and once we create the move assignment, we will eliminate this memory creation. And then we'll see that we, instead, what we'll do is we will take ownership of existing memory where we don't have to worry about hijacking memory, okay? Let me see here. Okay, let me walk through this again. Vector size 3, 15B. Get vector ret 3, 15C8. Move assignment executes. Temporary memory is being created for us, which doesn't necessarily have to occur. So it is occurring. Let me see. And then let me look at the output statements. We have 3 different regions of memory. We have 15BO, 15C8, and 15EO. So then, yeah, the diagram's correct. But again, unnecessary. Like, memory is already in existence. So why can't we just switch pointers instead of going through all this copy statements, right? Which, I mean, it's not C++'s fault. It's doing the best it can with what we have in our rule of 4, but we are missing the last rule, the rule of 5, right? So let's go ahead and do that. Okay, so we go and write some code, and we use another R value, and the code is similar to this one right here, to operator override, but with the difference that we are using an R value. Okay, so let me do that. So here we implement vector reference operator equals vector R value v move assignment rule 5 of 5 of the rule of 5, and that's for a modern C++. And then we go ahead and write code for this, and we'll also write down the steps we need to execute to make that happen. Okay, so make this part of our class, overload the equals operator with move, and then let's see what we need to do to clear that issue of the duplicate memory creation. Okay, that move constructor, it always has me second guessing. Okay, so we have a clear original dynamic memory, okay, and then 2 point elements to v dot elements, and then 3 get size from v, and 4 point v dot elements to null pointer, and finally 5 set v dot size to 0. Okay, so let's do that. Clear original dynamic memory, delete elements, point elements to v dot elements, elements equals v dot elements, and now I can write the output statement. Move assignment elements, so we can output the memory address. Okay, and then we have size equals v dot size, v elements to null pointer. That's step 4. Step 5 set v size to 0. V dot size to 0. Return a vector, so return dereference this, right? Oops. I was typing what I was saying. Okay, so once we do that, then we should eliminate the memory creation. But let's execute this now with the same code here, and then we'll go ahead and redraw our diagram. Okay, so let's see what happens here. Okay, so over here we had 1, 2, 3 different regions of memory, and here we have create memory 15B0, that one. Create memory 15C8. What happens in the get vector? This creation of vector. Move assignment 15C8. It's the overloaded equal sign, and notice now we hijack 15C8. Okay, so over here we had 1, 2, 3 different regions. Over here we have 1, 2, which is what we want. So now let's go ahead and diagram that piece. Okay, so class copy with move assignment. Class copy with move assignment. It's the same code, but now with the move assignment, then we won't be creating unnecessary memory overhead. Okay, so size 15BO, we'll use that one for elements. 1, 2, 3, 15BO, and then we have what happens in there. Size elements 15C8. Okay, and now let's trace that one, maybe with green. Okay, so let's go into the move assignment. Delete elements. Elements equals v dot elements. Okay, so which elements do we remove? Let's look at our code. Oh, where am I? Blue, right? Because we are overriding v. So this ones we delete. Okay, so delete. So this memory is available to use by our program. Okay, and then let's look at the other piece of code. Elements equals v dot elements. Okay, elements equals v dot elements. So we get rid of that one, and now that'll be what? 15C8. 15C8. So meaning now it's pointing there. And then it's saying size equals v dot size. So it's 3, right? That was going to be copied. Okay, so that one's taken care of. And then we're like, okay, v dot elements equals null pointer. V dot elements equals null pointer. So okay, so point to nothing, and then v dot size equals 0, 0, and then return the pointer, right? So now we have v, right, which is here, stealing the pointers or the memory that was created, and now we are not having unnecessary memory creations and copy. And let's go see our output to make sure 5C8 is left standing. So 15C8, right? So notice we are pointing to 15C8, and then memories try be free from 0, but the compiler's like, you're pointing to nothing, so it's okay, meaning this executes, right? Delete elements, but it's saying address 0, so C++ is like, oh, you're not pointing to anything. And then V is like delete, and then this is deleted before our program exits, right? So that is the move assignment in C++, and now we're not creating unnecessary memory loads and copies. Okay, so let me see if there's questions here. No. Okay, sometimes it takes a couple of viewings of the video, right, to understand what's happening here. Okay, so let me my mouth is getting dry. Okay, so we've covered the rule of 3. That's copy constructor, copy assignment, and destructor. Rule of 3 means that if you have dynamic memory, more than likely you need to implement those 3 concepts. Okay. Rule of 5 is for modern C++, and again, if you're using dynamic memory, you need to implement the rule of 3 plus the move constructor plus the move assignment to make sure that your classes are using memory efficiently and are not exposing themselves to memory leaks. Okay, so that's what we've just done. Notice up to now we've not added any functionality for vector. I mean, we're trying to implement the C++ vector, right? Granted, a very dumbed down version, the poor man's version, right? But it's okay, like it'll help us learn a lot. So now let's go ahead and do that. Vector pushback. So that's our goal. We want to implement the vector pushback. So let's start writing some code, and I'll be explaining it as we go along. Okay, so let's go here. And we'll add a new private data, size of t, space, and this is number of elements plus free slots. Okay, and I'll explain what that is. So then size is the number of elements. And if we have size, then space, then we want to be able to add another function that returns capacity. Oops, I meant to do that. Const, and we simply return space, right? So the capacity of the vector. That's what we are shooting for there. What time is it? 6:16. We have until 6:50. Okay, we should have time. Okay, so we have to go into our constructor and initialize space. So we'll just initialize space to incoming size, and We should probably do it here too. And oh, did I overwrite it? Okay. Well, we'll get free copies, so I don't have to go in and change everything. Since it's a stack variable, it'll be copied for us. Okay, so what does capacity do? So if we have capacity, reserve, and resize. Okay, so in a vector we may have, say, 1, 2, 3, 4, 5, 6. Maybe we have 1, 2, 3, 4, 5, 6 slots, but only these 3 are available to be written in. So 1, 2, 3, and then these ones are reserved, so the capacity of the vector is 6, meaning if we come here and we say push back 3 times, then we've exhausted the available elements, but we have reserved memory, and then we can do 3 more pushbacks before we would have to get new memory. Say we get new memory and this is 12, we get memory of 12 slots. We would have to copy all the elements to the new dynamic memory, and that's what capacity is helping us with, right? Like keep track of the total number of elements, and not all of them are available to be written. Some of them are just reserved. So once pushback exhausts its size, say size is 3, then it's like, okay, let me check if there's reserve. And if there's reserve, then it's like, okay, I can still use this block of memory here before I have to acquire new memory. So that's what capacity is helping us track, okay? Okay, so we have to implement the reserve function and then the resize function, and those two functions together will help us implement pushback, okay? So let's write the code for reserve and then we'll diagram it, okay? So we have void reserve, a simple function, takes in a size of t, and we say new allocation, right? New allocation size. Maybe we should put size here so that we know what that is, new allocation size. And then we come back and we write some code in the CPP, and those are class functions, okay? They're not free functions, meaning we have to make reserve part of our vector. Okay, so what does reserve do? Okay, so let's write that in comments and then we'll write the code. Okay, number 1, make sure new allocation is greater than space. Number 2, create temp dynamic memory of size new allocation. 3, copy values from old memory array to temp array, and then delete the old array, and then set elements to temp memory array, and finally number 6, set space equal to new allocation. Okay, so number one, make sure new allocation is greater than space, right? So there's different ways we can do that. So we'll simply say if new allocation less than equal to space and simply return, right? Meaning exit the function, don't do anything. Number two, create temporary dynamic memory. So create a pointer, name it temp, of new integers, and what size? New allocation size. Okay, and then it's saying copy values from old memory to temp array. Okay, so, and then we'll diagram this so you can see why we have to do this, right? And then you'll be thankful that the C++ programmers created smart pointer, string, and the vector class and all other list classes in C++ to make it easy for developers to program. Same thing the Python programmers did. Temp of I, they abstracted all the complexity so that you could just focus on learning how to program. Elements of I, fortunately this class, like, it requires you to learn about memory techniques, right? So that's why we have to go into these topics. So that's step 3. And step 4, delete the old array. Okay, delete the old array, which is elements. And then step 5, set elements to temporary memory array. So elements equals temp, and then space equals new allocation size. Okay, so let's, well, before we do that, let me see. Okay, we had new allocation. Yeah. Diagram time. Okay. Reserve. Assuming size was 3, and we'll stick to that address 15BO. We do 3 pushbacks. 1, 2, 3. We're out of memory. We're out of memory. We need more memory, right? So then we say, okay, I want the new allocation to be 6. Okay. So then we call this function, this class function with 6. So is 6 less than equal space? No. Okay. So we don't execute this P. So then we create new memory of size 6. Okay. So somewhere here we create new memory of size 6. 1, 2, 3, 4, 5, 6. Okay. And then we're saying copy elements from old array to new array. So we have, assuming all of them were zeros, right? So then we have 1, 2, 3. We copied 3. And then we have 1, 2, 3 free slots, right? So the capacity of this array, of this vector is 6. Delete elements. So then this was pointing there. This would be deleted, and then we would be pointing to the new memory, right? And then we set size to new allocation size. So then this one would be 6, and assuming this was like 15CO, 15CO, right? So it's pointing to new memory. Actually, I did this wrong, right? Not this one, but this one. And that's what's happening, okay? Why? Because we were granted 3 slots, but if we've exhausted them, then we can't write anymore. Like, we need to create another chunk of new memory. We double the size, and then we hope that that's enough, right? So, and actually, according to Bjarne Stroustrup, right, the creator of C++, that's how the implementers of the vector class did it. They're banking that the vector's not going to grow by multiples of 2, right? So then they say, okay, we can create a const integer reserve default size, meaning, like, if we don't have an allocation or if space is 0, then we can just guess and be like, okay, let's grant them a chunk of 8 slots of memory, okay? And let's hope that that's enough for now. If it's not enough, then what we'll do is we'll have another const variable, and we call it the reserve default multiplier. And here we'll say, well, I mean, whatever memory they currently have, we're just going to give them double the memory, which makes sense, right? Because if they have like a lot of memory, we can't give them like 3 or 4 times, right? So we're trying to be conservative, but at the same time not give them too small of memory chunk. Okay, so, and let's see how these guys are used, right? So actually these guys will be used in the other function resize, right? So any questions here on the reserve, like why we have to do it? Let's see here. No. Okay, so let's go on to resize then. So void resize, and again it accepts a size of t, a new allocation size. That's just the name of a variable, okay? And then we're like, okay, let's go ahead and create the resize function. And again, we will write step by step what this function has to do, and then we will also diagram it. And actually, this one's a lot smaller, right? So easier function to deal with. So we call reserve function with a new allocation size. That's the first step. Number 2, initialize elements beyond size. Let's go back to the diagram. Remember, we had 3, we doubled the memory, we now have memory of 6, so this one's assuming they were 0, right? But this ones are uninitialized, so whatever value is there when the memory is granted to us is still there. So the resize function will initialize these values to 0, okay? So finally, number 3, set size to new allocation. Okay, so let's see. Call reserve function. Okay, I can do that. And reserve, unfortunately, let me see. Okay, it is there. Actually, resize is not part of vector, so this one has to be part of vector. So now we should see the reserve. Reserve, yep, there it is, with new allocation size. Okay, so easy enough for us to do. Initialize elements beyond size, meaning iterate for size of t, I equals 0, I less than new allocation size plus I elements of I equal 0. Right, let me see here. This one should be size. Right, because if we come back here, size was 3, 1, 2, 3. So we 1, 2, 3. So we initialized this one. So we need to initialize beyond size. Okay, so that's the correct code. Not what I had there. And then set size to new allocation, meaning size equal new allocation size. And let me double check that that code. So now you should hopefully appreciate the string class, the vector class, smart pointers. They save you a lot of trouble, right? With memory leaks and stuff like that. So let me see here. I didn't feel comfortable. I don't feel comfortable with that code. I just want to make sure I'm giving you the right code. Yeah, it is size. Okay, so so again, size would work with reserve. Resize would work with reserve to grant us more memory. Reserve initializes the ones that are copies by copying them over, and then resize initializes the ones that are not initialized, just to make sure that our values, all values, have some good value that our program would use. Okay, so finally we can write the pushback function. And the pushback function uses those two functions to work, right? So we say, okay, so push back what? Some value. Okay, some value. We push back some value into our dynamic list. Okay, make it part of our class. And then what does this one do? If space 0, call reserve with reserve default size, meaning if space was 0, meaning like if the vector is initialized to nothing, then we need to do that, and we'll have to write the code for that in a little bit. So then number 2, else if size equals space, call reserve with space times reserve default. Default multiplier. And finally, increment size. So the space equals 0. Sorry, my bad. So someone's probably at the reserve default size. So we do that. If space equals size, or size equals space, then reserve with space times reserve default multiplier. So double the memory. We need to make sure that we set a value to current element at size. Okay, meaning elements at size equals value, right? That's how we push that value onto our vector, and then we have to increment size. Okay. Okay, and let's go ahead and create the default constructor. So we'll say vector. Okay. Why? Because remember, when we create a constructor, we don't know, we can just say like the data type, and then it creates a list for us that's ready to be worked on. Okay, so let's copy this into our CPP and create the constructor. So we have an initializer, and we'll say size is 0, space is size or 0, right? And elements is null pointer. So now in pushback, space and size are equal. And then it'll run this. Let me see. Oh, that'll always be 0, right? Space equals size. No, space is 0. Okay, space is 0. So then it'll grant us 8 slots of memory. Okay, so that should work. And we're going to test it. Okay, so let's see. test case. Okay, so let's see about this vector guy. Vector v should create an empty vector, push back value 2. So if our logic works, then we should say what we require is v dot size equals 8, and then we require that v at element 0 equals 2. Vector v dot pushback, v dot size should be 8, v of 0. Okay, well, let's run it, right? Questions here? We are not. We are not allocating on the heap the exact number of slots the vector asks for. I'm sorry, I don't know what section that was for, like what piece of the code. Okay, let's see what happened here. Ooh, failed. Let me see here. So v dot size equals 1. So let's see. V dot pushback 2. So vector v should execute this one. So size and, well, maybe this is wrong. Maybe this should be 0. Okay, so size space. Let me look at the pushback. If space is 0, reserve default size, which should be 8. Increment. Oh, okay, yeah. No, it's correct. My test case is wrong, right? So capacity should be 8 and size should be, actually it doesn't make sense, right? It does, because we have one pushback. Okay, yeah. Sorry, I'm outsmarting myself here. So the vector size is 1. Okay, so let's run it again. Run in terminal. And let me look at the code here. Reserve space is new allocation, so that should come out positive. Okay, so let's see what happened here. Thankfully, now it passes, right? So I just had the test case set up incorrectly. Oh, all those out statements. Okay. Up arrow space dash s, enter. We'll look at the last one. So v of 0 is 2, size is 1, and the capacity of the vector is 8, right? So that's in the definition of capacity, right? So capacity is number of elements plus the free slot. So 7 free slots and 1 element, so that's 8, right? So then number of elements 1, right? So I just had the test case set up incorrectly. So questions here? Okay, so what happened there? We have this vector v, but as you saw, like I had size of 0, space of 0, and we were pointing to nothing, right? Elements is pointing to nothing, null pointer. So temporarily the heap is not in use. But if I say v.pushback 2, then pushback's like, hey, I don't have any memory. Okay, I need to create some memory. And then we look at pushback. Space is 0, so then it's like, oh, I need to reserve memory. So default size, we know we had set it to 8. So then it's going to go out and seek 8 slots, right? So 1, 2, 3, 4, 5, 6, 7, 8. And they'll be initialized to, well, actually they're not initialized, right? So then pushback's here, so then that's size. So now size is 1, and space is free slots. 1, 2, 3, 4, 5, 6, 7, right? 1, 2, 3, 5, 6, 7, plus elements. So 7 plus 1, 8, and assuming this was like some address, we'll stick to that 15BO. And they will be pointing here, right? So now the memory is live, and each time we would do a pushback, like we would see a new address, a new value there, a new value here, a new value here, 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 and here, right? So let's questions. Oh, excuse me. So let me do this one. So we have vector v of v3, so 3 elements. Pushback 3. See out v of 0. And then see out v dot size, and see out v dot capacity. And let's go up here and run this one. Run in terminal. Okay, so we have let me see here. What happened here? Pushback 3, v of 0 is 0. That doesn't look right, right? And v dot size 4, v and 6. Okay, so let's see what happened here. So this constructor executes, and we have size to 3, space to 3, elements of 3. Memory created for 3, okay? And then we should have size 3 and space 3. So what went on? Oh, more memory was granted to us, right? So let's see over here in the pushback, but that should not be a value of 0. Space is equal to size, so then they get space times reserve default multiplier, so that's why we get 6, okay? And then the size is 4. There's something wrong with the logic here. Hold on, let me fix that. So this should be initialized to 0, right? Let me do something here. Pushback 3, so size 0, 1, 2, 3. size should be 0. Let me run that again. Yeah, that looks more like it, right? Pushback 3. So let me draw that here. So if we have a vector with 3 elements, so size should be 0 because we don't have any elements, right? We just requested 3 elements, spaces. And then space is capacity or free slots, right? Plus elements, so 3 plus 0, 3. And then we have 3 slots over here in memory. 1, 2, 3, 1, 5, B0, we'll stick with that guy. So now when I do pushback, then this one is 3. And this one changes to 1, and space is still 3. So let me go back and look at the output, and now it looks better, right? So 3, 1, 3. So the error, if you were following along with me with code, make sure this one is 0, okay? Because otherwise, what I was doing is we were trying to write over here, and we were given more memory, so we were not using the first 3 slots. We started on the 4th slot, which is incorrect. So now that's the correct code. Okay, any questions? And again, that was on me, right? Because what I should have done is I should have created a test case from the beginning, and then we would have found that issue right away. That's the recommended guideline, right, for the C++ programmers, right? Because if you're only going to use one value, then you do a pushback, then you've already exhausted your memory, and then you do another push, and then you have to create new memory again, get that value copied into the new memory, right? So you're doing unnecessary memory acquirement. So that's why they're saying that 8. I guess after studies of how people use vectors, they're comfortable that 8 slots should be enough to avoid all those new memory acquisitions. Every time we create new memory, we're moving around memory on the heap. Yeah, but in this case, we're not going to create new memory until we do 3 pushbacks here. Once we do 3 pushbacks, then we'll create memory. So if we go back to this one, right, we have 0, and then we push back, and then C++, our code's like, okay, we're going to grant you 8 slots. So meaning you can do 8 pushbacks before new memory is required, right? Yeah, I mean, even though memory is fast, like if we're constantly doing that and changing values all over the place, then we're creating unnecessary copies, right? So if we're only pushing one value to the heap, would it be better only reserve one space, right? So if we only have one space and then I do a pushback, then I try another pushback, then I'm out of memory already. So then I have to create more memory, right? So that's why we kind of guess, okay, 8 should be enough. Okay, so that's it. There's no class assignment today. That's all I have for today. We'll continue with finishing this vector class next week, and then we'll move into character arrays, and that should cover another lecture. So if you don't have any questions, then that's all I have for today.